The battery blame game, when it comes to electric vehicles or EVs, there's a common belief that's hard to shake. What we think we know is shaped by headlines, conversations, and the numbers we see on price tags. Whenever the topic of why EVs are so expensive comes up, one word almost always dominates the discussion: batteries. For years, batteries have been the single most expensive component in an electric car, packed with costly and sometimes hard-to-source materials like lithium, cobalt, and nickel. The auto industry has poured billions of dollars into making batteries better, safer, and cheaper. Thanks to this relentless innovation, we've seen huge progress. Costs have dropped dramatically, and energy density has soared, allowing cars to go farther on a single charge. This focus on battery technology has made EVs more practical, more reliable, and more accessible to everyday drivers than ever before. But what if I told you the battery isn't the only expensive secret hiding under the hood? There's more to the story than just the battery pack. There's another critical component, often overlooked in mainstream conversations, that's just as essential for making the car move. It's found deep inside the electric motor, the very heart and powerhouse of the vehicle. This story isn't about charging stations or range anxiety, but about some of the most powerful and specialized materials on our planet. Materials that are crucial, yet rarely discussed. It's a story about magnets, super strong, high-performance permanent magnets that make modern EVs possible. Let's dive in and explore this secret magnet problem and why it matters for the future of electric vehicles. Meet the unsung hero, the permanent magnet. Though small and often overlooked, these powerful components are at the heart of modern electric vehicles, quietly enabling the technology that's changing how we move. The permanent magnet is the key ingredient in the most common type of electric motor used in high-performance EVs, the permanent magnet synchronous motor, or PMSM. These motors are found in everything from family sedans to cutting-edge sports cars. Electric motors use magnetic fields to create rotation, spinning a central shaft that turns the car's wheels. This process is what transforms stored electrical energy into the motion that propels your vehicle forward. Many motors use electromagnets, which generate magnetic fields only when electricity flows through them. But these require extra energy, making them less efficient and generating more heat during operation. Permanent magnets, on the other hand, have their own strong magnetic field without needing electricity. This means they're always ready to work, providing consistent performance with no extra power required. By placing these magnets on the rotor, the motor becomes much more efficient. Less energy is wasted, and more of the battery's power is used to move the car. This means more miles per charge or a smaller, lighter battery for the same range. For drivers, that translates to longer trips and less time spent charging, making EVs more practical for everyday use. Permanent magnet motors are also power-dense, allowing for quick, responsive, and fun-to-drive EVs. Their compact size and high output make them ideal for vehicles that demand both efficiency and excitement. Without these special magnets, the performance and efficiency of today's leading electric cars wouldn't be possible. They're a crucial part of the EV revolution, powering vehicles of all shapes and sizes. They're the silent workhorses behind instant acceleration and smooth power delivery, making every drive feel effortless and refined. The battery stores the power, but it's the permanent magnets that put it to the road, turning electrical energy into the thrilling, silent motion that defines the electric driving experience. What's so special about these magnets? The rare earth recipe. Now you might be wondering what makes these permanent magnets so special. Why can't we just use any old magnet? The answer lies in their ingredients. The most powerful permanent magnets in EV motors are made from rare earth elements, specifically neodymium iron boron, NdFeB. These magnets are the strongest commercially available, creating powerful magnetic fields in a compact size. But to work at the high temperatures inside an EV motor, they need to be doped with even rarer elements, dysprosium and terbium. These secret spices help the magnet maintain its strength when hot. Without them, performance and efficiency would drop dramatically. This blend of rare earths allows for small, light, and powerful motors, delivering the acceleration and range drivers expect. The unique properties of these elements make them almost irreplaceable in this application. But this dependency is also a major vulnerability. The link between high-tech motors and the complex world of rare earth mining is direct and risky. Our reliance on these materials ties EVs to a challenging global supply chain. The problem isn't just that rare earths are rare, they're hard and expensive to mine and process. Most of the world's supply chain is concentrated in just a few places, especially China. China controls over 60% of rare earth mining and nearly 90% of processing and magnet production. This creates a fragile, risky supply chain for automakers worldwide. Any disruption, geopolitical tension, trade disputes, or policy changes can send prices skyrocketing and disrupt production. In 2010, a diplomatic dispute caused rare earth prices to spike by thousands of %, exposing the industry's vulnerability. Today, as EV demand surges, competition for these resources is fiercer than ever. The magnet supply chain is a bottleneck and everyone is feeling the squeeze. Automakers are acutely aware that the magnet problem could completely derail their ambitious plans for electric vehicles. The pressure is mounting as the industry faces a critical shortage of rare earth magnets, which are essential for the motors that power most modern EVs. Tesla, long recognized as a pioneer in permanent magnet motors, is now racing to design next-generation powertrains that are entirely free of rare earth elements. This bold move could help Tesla sidestep future shortages and reduce its reliance on unstable global supply chains. GM, meanwhile, continues to use permanent magnet motors in its Ultium platform. To secure its future, GM is partnering with magnet producers and investing heavily in building a robust domestic supply chain, aiming to insulate itself from international disruptions. Ford's Mustang Mach-E also relies on permanent magnet motors, and the company has already faced significant delays and mounting cost pressures due to ongoing supply chain disruptions. These challenges highlight just how vulnerable automakers are to magnet shortages. These companies are learning that having the best battery technology isn't enough. If they can't secure a steady supply of motors, their factories grind to a halt and production lines sit idle, costing millions. The humble magnet has now become a central point of strategic planning for the entire automotive industry, influencing everything from R&D to executive decision-making. In response, automakers are innovating with new motor designs, exploring alternative materials, and building more resilient localized supply chains to weather future storms. It's a high-stakes race against time, with every delay threatening to set back the entire EV revolution. The decisions automakers make now, whether to stick with rare earths or pivot to innovative alternatives, will ultimately shape the future of electric cars for years to come. The magnet squeeze is real, and it's forcing the entire industry to adapt at a pace never seen before, driving innovation and urgency. The next chapter of the EV revolution depends on how automakers solve this magnet crisis, and the world is watching closely. Can we build good electric motors without rare earth magnets? Yes, but there are trade-offs. Induction motors used in early Teslas rely on copper and steel, abundant and cheap materials. They eliminate rare earth dependency but are generally less efficient, especially in stop-and-go driving. Less efficiency means shorter range or a bigger, heavier battery. Switched reluctance motors, SRMs, are another option. Robust, simple, and low cost, with no magnets at all. SRMs can be noisy and less smooth, but modern controls are improving their performance. There's no perfect solution. Automakers are experimenting with hybrid designs and ferrite magnets, which are cheaper but weaker. The choice of motor tech is a balancing act. Cost, efficiency, performance, size, and supply risk. The race is on to find the best compromise for affordable, reliable EVs. Innovation is happening fast, but the magnet dilemma is far from solved. The future may be magnet-free, but we're not there yet. For now, rare earths remain at the heart of most EV motors. The demand for rare earth magnets isn't just from automakers. Wind turbines use massive permanent magnets to generate clean electricity. One large turbine can contain hundreds of kilograms of neodymium. As we build more wind farms, demand for these magnets will explode, putting green energy and green transportation in direct competition. Consumer electronics, smartphones, laptops, headphones use tiny rare earth magnets in speakers, microphones, and vibration motors. Billions of devices add up to a significant share of global magnet consumption. Defense and aerospace rely on these magnets for missiles, drones, and radar, where performance is non-negotiable. Governments will always prioritize national security, tightening supply for commercial uses. The magnet problem is a challenge for our entire high-tech society, not just the auto industry. The competition for rare earths is only getting tougher. The good news? We have options. First, diversify supply chains. Mine and process rare earths in more countries to reduce risk. Building new mines and refining facilities is slow and costly, but essential for stability. Smarter trade policies and international partnerships can help keep resources flowing. Recycling is another big opportunity. Most rare earth magnets aren't recycled today. Developing tech to extract and reuse these elements from old products can create a circular economy and reduce mining. Governments can help by incentivizing recycling and designing products for easier magnet recovery. Finally, innovation is key. Engineers are developing new motor technologies that use fewer or no rare earths. Research into new magnetic materials could unlock sustainable, affordable alternatives. By combining these strategies, we can build a more resilient future for EVs and all the tech that depends on these magnets. The solution will be a mix of smarter supply, better recycling, and bold innovation. The path to an all-electric future is clear, but not without obstacles. The magnet problem is a hidden challenge that connects science, economics, and global politics. Solving it is essential to making EVs affordable and accessible for everyone. We can't build a sustainable transportation system on a fragile supply chain. The price of an EV shouldn't depend on global tensions or trade disputes. This challenge pushes us to innovate, recycle, and rethink how we design and build our world. The magnet problem is an opportunity to get it right from the start. The journey to clean energy is a marathon, not a sprint, filled with unexpected challenges. By shining a light on these issues and working together, we can overcome them. The future of transportation is electric, and by solving the magnet puzzle, we can make it secure, affordable, and sustainable for generations to come.